All right, so the next speaker and the last speaker before lunch will be Christopher Rhee. He's at Wisconsin, and he's done some interesting work in theory and implementation of a variety of algorithms. He'll be telling us about Hazy, which will be designed to make statistical applications easier to build and maintain and work with.
Thanks, Mike. Yeah, so as Mike mentioned, we do a bunch of work in my group on machine learning kinds of tools, making things go faster, as you heard about in the last talk, very similar spirit kinds of things. But I'm not going to talk to you about that today at all. What I'm going to talk to you about instead is building applications with those tools that are easy to both deploy and then maintain over time. And this is one of the things that we're pushing on in this Hazy project. All right. So this Hazy project I started about 3 years ago. And it was really in response to two trends that I thought were important for the future of data management and building new and interesting applications. The first one is that data now are available in a huge number of formats, much larger than at any time before. For the last 40 years, we've been obsessed with sort of traditional record-oriented data. With the last 15 years, with the advent of the web, people started caring more about text data. But by volume, this is a small fraction of the data that's available to us to build applications. Today, you can build applications with video and audio, OCR, data from physical sensors. And it's not that in any way this data are new. People have been studying OCR for decades, or sensor models for decades. It's that there's an increasing amount of value in these new kinds of data sources. So, for example, OCR and document capture is a multi-billion-dollar industry where people are basically just scanning forms and integrating it with the rest of their database stack. My favorite example of this is things like physical sensors. So you've probably seen the ads with Flo from Progressive. Flo is going to come around and stick a sensor in your car. She's going to monitor how well you drive, and then she's going to price your insurance better as a result of that. And this is a pretty interesting application because it's both using sort of cutting-edge sensor models, well, that's what they like to do, and it's integrating it with very traditional business processing. It's like a SaaS Oracle kind of stack. So the second trend that was driving this project Hazy is one that I think almost everyone in the room knows about. And that's this continuing arms race that's been going on for a long time now to understand your data more deeply. Now, the reason I use the phrase arms race is that even incremental changes in how well we understand our data are believed to have huge effects on the things we're interested in, right? So if we understand the market slightly better than a competitor, we're going to capture that market, make $1 billion, and the other guy is going to be the also-ran. Or we're going to be the discoverer of the boson, and the other team is just going to be a bunch of guys who hid out in a mountain for a couple years. Okay? So, as been talked about in the program, statistical tools really are at the heart of data analysis, or modern data analysis. So it's not a surprise at all that if we're going to want to understand our data more deeply, we're going to involve statistics in some fundamental way. But it's also involved in data acquisition. The state-of-the-art tools for OCR and for speech processing and for sensor modeling, all when they bring in that low-level information that they translate into a higher sort of application-ready format, most of them use sensor models as well, use statistical models as well. So what the Hazy project is about is saying, well, okay, if we're going to build all of these applications and we're going to have them, spreading to every different kind of domain, maybe it makes sense to start to think about how can we build a system with them? How can we understand how to build these systems so we can maintain them and easily deploy them in our application of choice? So that's what Hazy is about. It's trying to find those common patterns in statistical applications that are deployed again and again and again. Okay? So we look for these patterns at 2 levels, very similar to the last talk, Alex's talk, where we're looking for those sort of 7 common patterns that are out there that if you can do these, you can really scale up machine learning, and these are the algorithmic patterns, and we work on those patterns as well. I'm not going to talk about those abstractions today. What I'm going to talk about is at a different level of abstraction, which is sort of almost at the programming language level of abstraction, which I sort of informally call slinging signal together. Okay? Now, originally what we were trying to do this is we were trying to build systems, end-to-end systems, and I'll show a live demo. We'll see if it works. I'll show a live demo in a bit where we're just trying to sling together all these signals. What we realized after we built some of these systems is that the ability, and this is something that a lot of people have noticed, the ability to combine more and interesting signals actually can result in higher quality applications as well. So it's kind of an interesting thing. So that's what we're going to look at. To put my thesis in this talk a little bit more bluntly, probably more bluntly than even I think is true, I'll say it like this. The next breakthrough in data analysis may not be a new data analysis algorithm. It's not a new way of adding on a regularizer or being able to process just a little bit faster. But the low-hanging fruit, the things that could have a tremendous sort of earth-shaking importance, may very well be in the ability to combine all the signals that are out there and build applications that are easy to deploy so that anyone can deploy them, so that they can be easy to maintain, so we can have these applications live for a long period of time and see a lot of signal. that may be where these kinds of next generation applications come from. And so what we want to understand in Hazy is, to what extent is that true? And if that is true, assuming it is true for the moment, what do we have to do, what research do we have to do to enable us to build these kind of techniques? So when we started this, we had absolutely no idea what this even really meant. So we just started building like maniacs, and I will only show you a very small fraction of the stuff we built. If you want to see more, we have tons of stuff on the website, and there's even more hiding in our lab. Okay? What I'm going to do is just show you one demo, which is this thing called Deep Dive, which we call slinging signal at scale. It's going to kind of be this web scale thing. So I'll show you it, and then we'll have a live demo, and we'll see what happens. It should be exciting. So Deep Dive was a system that was built with some DARPA funding. This problem called machine reading, which was one of the grand challenge projects. And the idea of the system was to build a system that is able to read large volumes of text and then answer sophisticated questions over those texts. Okay? This sounds like the intelligence problem. You can imagine why DARPA would be interested. So in the actual evaluation, which we had last year, you had to answer questions like this. List members of the Brazilian Olympic team in this corpus, some provided corpus of text, with their years of membership. Now, ahead of time, you didn't know you were looking for Brazilians. You didn't know you were looking for Olympic teams. You didn't know that you had to know, the years of membership. You really just knew that you needed relationships between people, and you needed to know about, named people that were out there. Brazil, Olympic team. Those are kinds of concepts that you had to learn about, nouns and their relationships, global political entities. Then you had to read through all that data, not knowing this question, build some kind of structured database, and then answer questions like this. Okay? So we built this thing. We did quite well in the evaluation. We were very happy with that. And then my students want to blow off some steam. So when they blow off some steam, we build demos. That's what we do in our group. So I'm going to show you a demo that we built and put on the web. So what we decided to do was to enhance Wikipedia. Wikipedia is a very high precision information source in the sense that people put in facts, and generally speaking, they're correct. And it's curated by a small group of people. So there are facts about Barack Obama. His wife's Michelle. He went to Harvard Law School. Okay? But there's no mention of all the places that fact is mentioned on the web, the recall, that's generated by literally billions of people, in web pages and tweets, events, blogs, all those different places. Okay? So very similar to kind of the intelligence problem, we thought, wouldn't it be cool if we just turned our system on and enhanced Wikipedia by reading all of this information and associating it in a Wikipedia-like interface? And that's what this deep dive system is. So it's publicly available. I'm going to give you a demo in a second. Please don't go there now because you may knock it over. But what it is a framework for a sort of scalable probabilistic inference, which we'll talk about in the second half of the talk. And the other thing is taking just the best of breed tools that are out there, like Chris Manning's NLP tools, and running them on a bunch of stuff, or co-reference tools, and stitching them together to build these kinds of demos. Okay. All right. So here's an old version of the demo. This is actually over a dated crawl. This is a crawl from 2009. And what you see here is Barack Obama's page. And it says we found him in so many documents, so many sentences, so many videos, and so on. So this is getting at that high recall, large number of sources. The crawl is very old, so you see that this is a 2009 crawl. We have an updated crawl, don't worry. Where you have Hillary Rodham Clinton and John McCain. This was around the time of the election. So these are the related entities to Barack Obama. To show you that it's not doing things like just simple string matching, there are sentences like this that it says, this is provenance that actually Barack Obama and Hillary Clinton are related. It says, has he forgiven Barack for trouncing good old Hill, otherwise a shoo-in for heading the demo ticket into this election? And it's resolved that good old Hill here is actually Hillary Rodham Clinton, which it correctly is. And if you look a little bit deeper, that he is Bill Clinton. And it's built up a statistical context to do this. And how has it done it? It's used a bunch of NLP tools and a bunch of statistical inference stuff, which I'll talk about next. Okay. What's perhaps more cool is this info box here, where we have different relationships that are in text, like Barack Obama went to Harvard Law School. And we can click on this. This is too small to read. But there are sentences that are poached from web pages. And the new UI is better, so you can see actually where they came from. But it says, like Obama, Sunstein is a graduate of the Harvard Law School and is well known in intellectual circles in Chicago. Now this sort of clue, like Obama, you see it has to do some sort of linguistic co-reference. It has to do a bunch of reasoning. And this is sort of hand-picked to show, oh, it can do some sophisticated reasoning to establish the relationship that Barack went to Harvard Law School. But remember when I started this whole thing, I told you that I wanted to be able to do this across all kinds of different data sources. So here we are doing it across video, and it's not on a transcription. It's actually on the audio that comes out of the video. We're going to extract that Barack Obama went to Harvard Law School. So watch this video and wait about 10 seconds. Some mic problem?
Looks kind of like me. And if he's elected, I feel that I could be elected to president too.
They have something else in common, too. His mother is from Kenya, just like Barack Obama's father. And his parents, like Barack and Michelle Obama, went to Harvard Law School. But all those things in common aren't that important to 13-year-old Veronica.
Okay, so what happened there, it was actually the same linguistic pattern that we found in the text, the same like Sunstein, but we were able to discover that actually in the audio of the video, right? And how did we do this? We just slung together a bunch of those different things that are already out there. There are state-of-the-art things to do speech-to-text transcription. We do a bunch of those. There are state-of-the-art NLP tools. We put those together. Now, the problem is these different tools will make all kinds of conflicting judgments about actually what's going on inside the system, and we'll have to resolve those. And that's where the probability theory stuff will come in. Okay? All right. To give you a size and scale of what's going on here, the simple demo has about 50 terabytes of data. We're well beyond that now, which is very expensive to keep around. This is not for the faint of heart. It took about 500,000 machine hours to build, and we're well over into the millions of machine hours now, thank you to the Condor people. The point that I want to make, though, is that the code that actually runs this, like there's a lot of machines, there's a lot of systems engineering stuff, but the code that actually runs this is relatively compact. And it's because we're able to declare, graphical models, or however you want to think about it, declare these kind of probabilistic programs very, very simply. And so those are the kinds of abstractions that allow us to sling these things together. Okay? So even though there's a huge, huge array of tools and data and all this stuff flowing around, actually 2 graduate students built this whole thing end to end. Okay? And I think that speaks to the power of the abstractions that they developed in the course of their research. Okay? Now still, even though you see all the front-end stuff that we're using, even still this is great, but it wasn't really our goal. The goal of our work was really to take these kinds of tools and turn them into commodities. And we're not quite there yet. We don't actually know how to do that. But I'll tell you about a little bit of progress we have, because again, what we do is basically build things. And then I'll talk about some technical stuff in a minute. Okay. So one project that we have that's very related to this is this project called GeoDeepDive, which will show up in a second. So here's GeoDeepDive. What it actually is this is in a collaboration with some geoscience people, Shannon Peters, who's in the Wisconsin Geoscience Department. And what he wants to do is read all of the geology literature and find out all the different measurements that have been recorded about different rock formations in North America. So it turns out that researchers can't actually get a very good measurement of how much carbon is in North America. No one has this laying around in their lab. But if they look into the literature over the hundreds of thousands of articles, about 200,000 articles that are published, this information is just ready and waiting for them. But they have to figure out how to extract this information from tables and figures and graphs and charts and actually in text. And people refer to this carbon in pretty circuitous ways. The cool thing from a CS point of view is that actually the hope is by the end of the summer, they'll be writing all the code. We will just be maintaining the framework and doing some infrastructure stuff that they want to do, and we've hopefully pushed it over the wall. Okay. Another one of these examples is in IceCube. This is a thing we work with, which is a neutrino detector. And here, again, we decided to replace a complex physical model of how neutrinos interact. So what IceCube is a block of ice at the South Pole. It's about 2 kilometers long. Its job is that when neutrinos or very high energy particles come in, its goal is to regress out their energy, their path, their trajectory, so that they can study the properties of the different high energy neutrinos. Now, we did not know anything about physics, but we were able to robustly acquire a bunch of different signals and quickly sling them together. And that allowed us to replace their detector software. And by next year, it will detect about 100,000 neutrinos and is actually running on the South Pole. Okay. So the message, the takeaway from this, is that really these sort of data management ideas, the ability to quickly sling together things and easily maintain them over time, plus statistics, is hopefully going to open a huge number of new applications. Okay. If you believe that there's really going to be this big data revolution kind of coming, then what you may want to do, or one step that you could take in research, is to try and come up with a framework that allows you to rapidly combine and deploy many of the existing algorithms. Now, we don't know what the right framework is. We're just building as many as we can and refactoring, and they're not really coming together. They're more congealing in the lab, so it's kind of a mess. But what I'm going to tell you about now is one very simple framework that we have to bring these signals together. And because we've been talking at a high level, I may actually show you a proof at some point of some new technical result that I think is cute. Okay. So the framework that I'm going to tell you about is this thing called elementary, and this is what's backing up all of those different examples. Not the IceCube example, actually, that's hand-coded stuff, but the GeoDeepDive and the DeepDive example are both written in this very simple framework. So what it uses is this language called Markov logic that was developed at Washington, which is University of Washington by Pedro Domingos. It's a very simple language. It's basically first-order logic with some weights. So the top rule there says students tend to be co-authors with their advisors. Okay, so these are logical rules or logical implications, but they're allowed to have weights. They don't have to be perfectly correct. Okay, and those weights can be learned or they can be set by hand. Then the other thing you'll have is a bunch of evidence or observations about the world, and you're going to stitch them together essentially with these very high-level language that's going to allow you to talk about this. And this is, by the way, just one of a flavor of these languages that's trying in some sense to capture like a logical kind of syntax or a programming language kind of syntax with some statistical reasoning to make it easier to deploy. There are many of them. Okay. So these in particular have a very simple meaning. They basically declare giant exponential models. Okay? So they're basically factor graphs, which I'll illustrate in a second. You basically take every variable and fill it out and create each variable creates a node, and then you create a giant factor graph where they're tied together if they appear in some rule together with a weight that's given by that number there. Okay? There's some justification for this in statistics, but I'm not going to give it to you. Okay? So how does this actually work? So before we started this project, these languages had really been confined to 100 or 1,000 different documents. They weren't able to scale up to the web. So how do we get these things to scale up to the web? Well, there are two phases actually when you want to do inference or a subpart of learning, which work like this. You take the rules and you ground them. You replace them, as I said, with all these different constants. That's semantically what they mean. You don't have to do it this way. This is the same as generating a giant Markov random field, factor model, graphical model, whatever you want. The individual facts here correspond to nodes, and the edges or hyperedges of this graph correspond to those different rules, and they're weighted. Okay? And they can be more complicated than just simple weights. They can actually be functions that you call. Okay? Then, after you've created this graph, you basically run some kind of sampling algorithm over it, a Gibbs sampling or an MC-SAT sampling, some kind of sampling to try and generate something. Now, we prefer Gibbs, and I can tell you why later. Now, what it turned out for these particular class of languages is that data management ideas helped a lot, and I'm going to be able to show you that with the time remaining, in the grounding phase. It turns out, sort of less obviously, they also help in the sampling phase. And by help, I mean be able to scale these things up and run faster. And as you know from things like sampling, if you can run faster or achieve higher throughput, you can also sometimes get higher quality as well. And that's a point we can come back to later. Okay? But I am going to show you the grounding, primarily so I can show you this theory result that I like. So how does it work? Okay? So the first stage is not theory at all. Okay? We have this Markov random field. We have this graph that's there, and it may be much, much larger than main memory. How are we going to operate on it? Okay? So it turns out that actually creating that graph is a bottleneck in a lot of these applications. It would take 95% of the time just to construct this huge graph, which they would only sample from a couple times. So it looks a lot like if you're familiar with Datalog versus Prolog, which are these logic languages, and databases basically came up with very clever ways to create graphs or relational structures. So how could this actually help? Well, what we did in a system called Tuffy was just translate them, and that's a very simple language there. That's SQL, if you don't know it. It's a very simple database language that Oracle speaks, and MySQL speaks, and Postgres speaks, and Greenplum speaks, all those people. And then we just use what a database would do. Okay? And what a database would do here is when it's given that query, it would be able to correctly manage main memory and cache and all those things we heard about in the last talk automatically just from that declarative language spec up there. Okay? So no theory at all, nothing, just implementation. You get about a 2 order of magnitude speed up just from paying attention to things that are sort of classical database management challenges. And if you really care, the difference here is that you're able to do these things called joins, which we'll talk about in a second, much, much more efficiently than the naive way, the naive n-squared way of doing them. All right. Okay, so a little bit of theory, because I've been talking at too much of a high level and it's kind of making me sick. So here's some theory, okay? If you haven't seen this syntax before, this is a logical query. What it's saying is it wants to find all the triangles. If I imagine C as an edge relation of a graph, it says give me all triangles, okay? So for example, I could find all co-referent triples on the web. This is something we have to do. All 3 things, triples that co-occur on a web page, something like this. Okay? So if C contains n tuples, how big can the output size of R be? So if you look at it sort of naively, the first, maybe most naive thing you say is n cubed. You just multiply them all together, right, each instantiation. And you think, well, that's probably not very accurate. The first 2 edges probably cover the last one, so n squared. Well, it turns out that this question has been studied since Erdos and Rainey for a long time. And it's roughly known that the right asymptotics here is that the size of R is about n to the 3 halves. Okay? And you can be more precise than that if you really wanted to be. Now, this inequality here that states this can be generalized in all kinds of ways. In discrete geometry, people call it Loomis-Whitney or Bullebosh-Thomason. Loomis-Whitney is from like the 40s. Bullebosh-Thomason is from, I think the mid-90s. It was also sort of rediscovered in a different vein, a different spirit by the stock Fox community, and was called the fractional cover inequalities. At Sirius et al. Had a bunch of papers about this. Very, very cool stuff, okay? Basically generalizing this kind of cover, fractional cover idea, to all kinds of relational queries, just like we saw. Now, although we could bound the time to the size of R, we couldn't compute it actually in that time. So the question that I'm going to show you is, can we be able to compute R in time n to the 3/2? Okay, so can we compute it much, much faster, which is that core grounding operation that I talked about in the deep dive and the toughy kinds of systems. And actually, by way of showing you this algorithm, which yes, of course we can, I'm going to give you a very simple proof of this inequality that hopefully will allow you to generalize to other cases. Okay, so here's a very, very simple algorithm that allows us to run in time n to the 3/2, which is actually worst case optimal. Okay. So the main extremely simple idea is to take every node in the graph and call a node heavy if it has more than square root of n neighbors. Okay. And let's ignore log factors because they complicate things and you can get rid of them with some sweating, so let's just ignore them for now. Okay. So how does this algorithm work? So in case 1, what I'll do is I'll take all the nodes that are heavy, and I'll check to see if they form a triangle with any node that occurs in my listing C. Okay? So how do I have to do this? I look at each edge, I look at my node, and I have to probe into the, think about it as a hash table, to see if each of the 2 other directed edges are there. Okay? This can be done in constant time for each heavy node. Okay? So since I have to scan each of the relations, and I have to do each of the heavy nodes, then this takes time n times h. But since the size of h is less than square root of n, because its fan out is square root of n, so there could only be at most square root of n of those guys, I can do this step within the time bound. So that leaves case 2, when v is not heavy. And here what I'm going to do is I'm going to hash each pair of nodes that are leaving them, so each in degree and each out degree. Okay? So the running time of this is going to be the in degree of every node, the sum over the in degrees of every node, times its out degree. Okay? Now, a simple 1 infinity holder tells you, since the out degree of any node, or the degree of any node, is going to be less than square root of n, and the sum of the degrees is less than or equal to n, this is going to be less than or equal to n 3/2 also. Okay. All right. And now that I have these 2 things, which actually happens to be disjoint, but you don't need it here, I can take their output, and lo and behold, I got this in n 3/2 time. Okay. All right. So this is extremely simple, but I'll tell you why it's interesting in a second. Okay. So the positive result, which just won a recent best paper, is that we can generalize this to arbitrary join queries. So all the different join queries that we would have, that logical language that we would have, we can actually get them in best, worst case time. This is actually, what I just showed you is actually the first step, the very simple step, of a constructive proof of what's known as Loomis-Whitney, so the first constructive proof of Loomis-Whitney. And we generalized to all of Bolobash-Thomason and actually showed that these 2 areas, the stock Fox people and the discrete geometry people, actually were working on a very similar problem, and we linked them up in a couple of paragraphs. Okay? And then there's the theoretician's cop-out. That's the same intuition, only much more involved. Okay? All right. Now, why this is actually interesting for us is that the negative result, which is that any database query plan, all those ones I told you were so smart and were singing their praises just a little bit earlier, actually are all asymptotically worse than the plan I just showed you. And in fact, you can always construct instances actually pretty easily where on the triangle query, any database on the market right now will run in time n squared. But this algorithm avoids that case. Okay, so with that, I'm going to skip through a thing about sampling and calibration. So one thing I didn't get a chance to talk about here in any real detail was that there's a bunch of work that's gone on here about both sides of this. Building applications, so populating knowledge bases from text, things like sucking in data in all kinds of different data formats, different machine learning algorithms, and also a whole bunch of theory. But it's all towards this common goal of trying to make data analysis really a commodity. Okay? And there are all these little pieces and subproblems that fall off when you actually start to go ahead and build these things in your lab and get support very mad at you. Okay. All right, so in conclusion, I argued that the next breakthrough is the ability to quickly sling signal at scale, by which I mean bring in as much signal as possible, and it raises a host of new challenges and a bunch of classical challenges as well. But that getting more data into your system scalably and quickly and sort of optimizing for programming languages is one reasonable way to do it. Today I showed you one of our first initial guesses about how to do this, which is a framework called Elementary, which you can download, by the way. All of these things are downloaded. All of our data is available to be downloaded, all of our code called Elementary, which you can download and run. And actually, I just know another group who sent me an email today that they got their own version of Deep Dive running on their local servers on one pretty beefy machine, but still just one machine. Okay. So with that, I'd like to thank our sponsors, and that's it. Thanks so much. Absolutely wonderful question. So the question is, here it seems like you've cherry-picked the fact, and we did cherry-pick the fact, that we were looking at the English YouTube. What happens when you look at text that's either in other languages or substantially degraded, right? Like you're looking at Twitter feeds. So there are two things there. One is the holy grail would be exactly what you're hinting at, to automatically detect that and sort of appropriately route it to the right smart algorithm. The other approach that we use is actually just to try every hammer we possibly can on it. Just blast it with everything we know, and then look at how coherent it is when it comes back. So if you send out the translation and it doesn't satisfy some very minimal coherence, this is not implemented, by the way, but this is like the working strategy in the lab. That's what you would be able to do. So we would love to get to that automatic version of it, but for things like where the precision really matters, we would just allow you to write a simple rule that says, if it has the following majority language classifier, page says blah, then we would do it. But great question, and that's actually a direction we definitely want to head, is across languages. So I think data management has been pretty well commoditized. There are things you can buy and download to do a lot of your data management needs right now. So my goal is not to be the next Oracle, because Oracle I think may be in the room and they sponsor my work. No, but the goal of what we're trying to do is take those things that actually are going to contribute to traditional, like what people are going to do in an enterprise, and put that into the pipeline. So when I say make a commodity, what I'm really getting at is, if you go to an enterprise, they're not going to be able to hire the top flight machine learning or stats PhDs. They just can't do it, right? You go to an insurance company, they can't do it. So they need to be able to deploy these tools. And what my bar for commodity is that they can reasonably hire a team of consultants and a company to come in and do it for them. And right now, having gone inside some of these companies, they're very far from that goal. So it looks to me like there's a research gap between it. So the commodity is a fuzzy notion. It really just means that we can maybe raise by an order of magnitude the number of people who can do it. It's not the dream that all 7 billion people are going to be doing machine learning tomorrow. That's not my goal. Great question. Oh, great question. So the first question, does it make Tuffy obsolete? Everything makes Tuffy obsolete. We're a research. Everything's planned obsolescence. So for all funding agencies, Tuffy is totally, you don't want that anymore. You want the new thing. No, the systems that's in there, I mean, practically there's a huge number of leaps that you have to go through before you're able to reliably deploy joint algorithms in practice. And so we're working with some commercial partners to try and figure out if the theoretical algorithm actually brings real substantial practical benefit. So I don't think it's in any of the database vendors are in any danger of getting scooped by our new theoretical result. The second question you asked is sort of a more fuzzy question, which is, have you learned anything sort of interesting from building these systems? And certainly in each one we have, but they have sort of come out to be sort of life lessons. Like in the physics domain, what we've learned is that it's very difficult to debug your models, especially if you have a very high confidence in them. So for example, physicists really believe in their physics, which they rightly should, but if there are problems with the model, it's very difficult to trace back. So that's sort of a human nature thing. But as far as sort of facts that we've learned that are interesting about the web, nothing's really coming to mind at the minute, but I'm sure if you ask my students, they have all kinds of crazy things they hid from me.